This is lecture 7b on the integrals of trigonometric functions. There are two cases in which integrating trigonometric functions is easy and straightforward. In one case, you are given exactly the derivative of one of the functions that you know. For example, you're trying to integrate, let me get the highlighter here. If you're trying to integrate the cosine, well, you know that the derivative of sine is cosine, and you can evaluate that fairly easily. Similarly, secant squared, the integral of secant squared is tangent. There are other integrals involving trigonometric functions that are fairly easy, and these are the ones in which substitution will work. For example, here I have sine raised to the third power plus sine squared, but I also have a cosine x term with it. Okay, so I can use the substitution that u equals the sine of x because du equals cosine x dx. I've got the dx there. So you can rewrite this integral in terms of u, solve it by the power law, and then reverse the substitution. In this lecture, we're going to consider some other cases that aren't quite so easy. We're going to consider cases in which you have odd powers of sine or cosine or even powers of sine or cosine, and substitution is not going to work. Right? Those integrals we'll show you how to do those now. Secant and tangent follow from the same ideas that we use for the sine and cosine. And then we're going to do the integral of sines and cosines of different frequencies. This has importance in engineering. So here we're going to integrate sine function raised to an odd power, odd greater than 1. Okay? So here's sine to the 2n plus 1 or cosine to the 2n plus 1. And there is a procedure for being able to evaluate these integrals. And it involves first isolating one of the sine or cosine functions. So I have sine of 2n plus 1. I can write that as sine 2n times the sine of x. This, of course, can be written as sine squared raised to the n, and then I have the sine x here. Similarly, with cosine to the 2n plus 1 is cosine to the 2n times cosine to the first power. Cosine raised to the 2nth power can be written as cosine squared raised to the nth power, and then you have this other term, the cosine x isolated. Let me underline those. So you've isolated one of those terms, and you're going to use those to get yourself a setup for using substitution. So that's the first part. Isolate one of the sine or cosine functions, then use this identity, the Pythagorean identity, for trigonometric functions. Sine squared plus cosine squared equals 1. All right. So the sine squared here is replaced by 1 plus cosine squared, and the cosine squared here is replaced by 1 plus minus sine squared. Now you're set up. You have a setup now for using substitution. If u is the cosine of x, we have du equals minus sine x dx. All right. So here's my u term is here. Of course, u squared raised to the nth power, and then I have sine x. I'll need a negative sign. But I'm set up for that. Similarly, in this one, you would use u equals the sine as a sine function, and then du, of course, figure that out, is a cosine of x dx. And so here, this gets replaced by du. The sine squared gets replaced by u squared, and that's easy to evaluate, although you might have to use a binomial theorem to expand it, and you hope that n isn't a very large number. This procedure works for integrals in which you have one of the terms. You can have cosine and sine terms present, but you have to have something raised to the odd power, either the cosine or the sine, or in this case both, to apply that technique in the previous slides. And what that technique does, remember, it gives you a setup to use substitution. Here's an example. Let's say we have sine raised to the 5th power. All right, we isolate one of the sine. Here it's sine x dx. We want that, and so now we have sine to the 4th power, which I write as sine squared times sine x dx. Here's my trig identity. I replace sine squared with 1 minus cosine squared of x dx. Now I use the substitution. U equals cosine x du equals sine x dx, and now I have the integral from 1 minus u squared raised to the 4th power du. This is just going to be a polynomial expansion and then solved by the power law. Then you can substitute back. Here's a second example. Alright. I have sine raised to the 95th power. Well, that looks pretty horrible, but I do have a cosine around, and actually that's going to help me out. So I isolate one of the sines, okay, and so now I have sine to the 94th, which I can write as sine squared to the 47th power cosine x sine x. Alright, now I'm going to use sine squared plus cosine squared equals 1 and rewrite this sine squared term here. See sine squared? Where is it? There it is. Sine squared as 1 minus cosine squared times cosine x sine x. Now I can use a substitution. U equals a cosine x du equals minus sine x dx, and rewrite this, and this turns out to be very convenient for us, as you need a negative sign, the integral of 1 minus u squared to the 47th power times u du. You can integrate that by making another substitution, or you can just do it by observation. And of course you could back substitute. So again, these the way we change these powers around sets it up for substitution. Now when the only even functions, even powers are present, then using that that Pythagorean theorem doesn't work. Instead, we use a half angle identity. So because we have even powers, sine is raised to the, for example, 2m, let's say cosine to the 2n, then we can do the same thing before, where we break the sine squared and the cosine squared terms out. Now you can recall the half angle formula. Sine squared x, which is of course what we're dealing with here, is equal to 1/2 times the quantity 1 minus cosine of 2x. Also, cosine squared of x is equal to 1/2 times the quantity of 1 plus the cosine of 2x. So we'll use that substitution, and now we have terms involving cosines only raised to different powers, and of course we'd have to use the binomial theorem, and actually we can do something else at this point. But sometimes you have to keep doing this identity several times, which I'll show you one of those in a second. But actually here you're going to have to use the binomial theorem. You could use another substitution, but you need the binomial theorem now. And that isn't, it's messy, but it's doable. Here's an example where you have to use that identity twice. So we start with cosine raised to the 4th power. And of course we'd write this as cosine, whoops, there's a pin, cosine squared squared. Then we use that half angle identity to write cosine squared as 1/2 1 plus 2 cosine x, and that's what's substituted right here. Right, and that's squared. Now if I square this out, I'll have a 1. I'll have 2 cosine 2x. We're fine with that. And then I've got a cosine squared of 2x term. Okay, now I've got to do something about this. Here's cosine to an even power. I have to break this out using another application of this identity. So cosine squared x is 1/2 1 minus the cosine of 2x. In this case, the argument is 2x, so this becomes 4x. Okay, and now here's our original integral. Is equal to 1/4 times 1 plus 2 times the cosine of 2x plus 1/4 times 1 plus the cosine of 4x dx. And so it took 2 applications of that identity in order to get this into a form that we can solve easily. I'm just going to mention briefly integrals that have secant squares and tangents to various powers. In this case, we're going to use this identity. Secant squared x minus tangent squared x equals 1, which is just a Pythagorean identity. You know this. if I have sine squared x plus a cosine squared of x equals 1. So I'm using this Pythagorean identity, but I'm going to divide by cosine squared x. And this is divided by cosine squared of x, cosine squared x, and that's where I get this identity right here. Okay? And that's used when you have powers of tangents and secants. Let's look now at another application for these trig identities, and this is the important case and frequent case in which sines and cosines of different frequencies are multiplied together and then integrated. So various signal processing problems might have terms that look like this. Let me get the pen. All right. So I have sine, and then I have two frequencies here. One is m and one is n. Or cosines multiplying cosine, or cosine times sine, but the frequency is not the same. So what we do in this case is use those trig identities for the products. So sine of mx times the sine of nx, two different frequencies, is 1/2 times the cosine of the difference of the frequencies minus the cosine of the sum of those frequencies. Cosine and the two cosines become 1/2 times the sine of the difference plus the sine of the sum. And sine times cosine, we have an identity for that. So these are three common trig identities, and that's what we use on these integrals in order to solve them. And here's an example. Say I have the cosine of 120 pi t times the cosine of 180 pi t. So this would be 60 cycle. Oops, where's the pin? So this is 60 cycle, 60 hertz here, and here's 90 hertz. Okay. And we have these two sine waves multiplying each other. So we go back, and if we remember that the sine of the two frequencies is the cosine of the 1/2 times the cosine of the difference minus the cosine of the sum of the frequencies. Okay. So if we apply, sorry, I erased the board there. Okay, so I've got sine of omega 1 times t times the sine of omega 2 t equals 1/2 times the cosine of the difference, omega 1 minus omega 2, times t minus the cosine of omega 1 plus omega 2 times t. Remember, here we're adding the angular frequencies omega, not the frequency in hertz. That's why I'd written up here before. This frequency in hertz is 60. This frequency in hertz is 90. Instead, we're subtracting the coefficient of t. All right? And notice that here you would have a negative value for omega 1 minus omega 2. However, sine's an even function, so we don't have to worry about that. We should have 1/2 times the cosine of 60 pi t minus the cosine of 300 pi t. Those can both be integrated easily. You can do substitution if you want, or you can do it by observation. And that's the answer. So that is how that case is handled.